Good day everyone, and welcome to my YouTube channel, and welcome to another episode of Visuals With Maan. So in this video, we are going to discuss and compare the infinite product of the Modified Sierpinski Carpet and the infinite Wallis product. So this is in preparation for our navigation of the components of a Streamlit-based visual app generated using a Python script. Alright, so how are we going to construct a Modified Sierpinski Carpet? Alright, so we construct a Modified Sierpinski Carpet by iteratively removing central regions of a square. And at each step, the square is subdivided and parts are removed according to a changing ratio. So our keyword here is that we will be able to observe a changing ratio. And now we're going to compare the two versions. Okay, so we have the classical Sierpinski Carpet version and we have the modified version. Okay, so we'll start with the classical Sierpinski Carpet. For the classical Sierpinski Carpet, we're going to divide the square into a 3x3 grid and then remove the center square and repeat forever. And since we are taking out a fixed percentage from a square, then the remaining area vanishes entirely to 0. And now for the modified version. For the modified Sierpinski Carpet, the grid changes at every step from 3x3 grid to 5x5, 7x7, 9x9, and so on and so forth. And because the removed center hole or centerpiece gets progressively small, okay, the area never disappears. Instead, it goes down, stabilizes into a finite, non-zero limit. And now let's look at the math behind the twist, okay? Alright, so here is the formula of the Modified Sierpinski Carpet, okay? So we have here A sub n. This is the area of the current level. So the area of the current level is equal to the product of two factors. We have the area or the remaining area of the previous level denoted by A sub n minus 1 times the remaining fraction 1 minus 1 over r squared, where 1 over r squared represents the central square that we are removing. So unlike the classical Sierpinski carpet where the area vanishes to 0, changing our structural grid dimension Rn dynamically at each step prevents the area from vanishing, allowing it to converge into a unique non-zero limit. Alright, and now let's have a concrete experience through this numerical example so that we would know how these iterations actually behave. We'll begin by having an initial area A sub 0 equal to 1. Okay, and for the first iteration, n is equal to 1 and the grid is 3. So our R1 is 3 or R sub 1 is equal to 3. Okay. So to compute for the area of this current level, we follow the formula, this one, and we substitute the values. So at level 1, the previous area is 1, okay? And then n is equal to 1. So the remaining fraction will be computed through this one. 1 minus 1 over 3 squared. And 1 over 3 squared is 1/9. Okay, so 1 minus 1/9 is 8 over 9. Breaking down 8 over 9 into factors, so we have 2 times 4 all over 3 times 3. Alright, and now for iteration number 2. So our n is 2 and our grid is 5 by 5, right? So our r is 5. So the area of this level, denoted by A sub 2, is equal to previous area, which is 8 over 9, times the remaining fraction, 1 over 1 over 5 squared. So we have 1 over 1 over 25. So the remaining area will be, or the remaining fraction will be 24 over 25. Okay, so for the numerator, we have the factors 2 times 4 times 4 times 6. And for the denominators, we have the factors 3 times 3 times 5 times 5. Okay, and then computing the product, we have 64 over 75. So that's for level 2. Now for level 3, iteration number 3. So n is equal to 3, and then our grid is 7 by 7. So R3 is 7. Okay, previous area A2 is 64 over 75. And the remaining fraction 1 minus 1 over 7 squared, that would be 48 over 49. And breaking it down to factors, we have this notation here. Okay, so for the numerator, the factors are 2 times 4 times 4 times 6 times 6 times 8. And for the denominator, we have 3 times 3 times 5 times 5 times 7 times 7. Computing this operation, we now have 1024 all over 1225. Alright, now let's discuss the Wallis product. Okay, so the Wallis product will converge into a value same as pi over 2. Okay, and it will be computed using this infinite product. So this notation here, it's very beautiful, right? It means infinite product. So we keep on multiplying products using the iterations of this formula. Okay, n equals to 1, n equals to 2, and then you compute by substituting n's, and then we multiply the terms, okay, the iterations. And then upon performing the infinite product, then we will be able to observe this pattern. For the numerator, we will have 2 times 2 times 4 times 4 times 6 times 6. And for the denominator, we have 1 times 3 times 3 times 5 times 5 times 7. And what did you notice? Okay, the pattern looks like similar as what we have in the Modified Sierpinski Carpet, right? And now we have here the numerical example for the iterations of the Wallis product. Okay, so we can see here the decimal results. So for iteration 1, the value is approximately equal to 1.33. For iteration 2, it's exactly around or approximately equal to 1.4222. And for iteration 3, it's approximately equal to 1.46. So we can really see here that the Wallis product are expanding, right? So we can see that it's growing larger at every step as it climbs towards its final limit. Now for our core discovery, okay, we are connecting the area at the infinite level to Wallis product. Okay, so again, this is the formula or the notation in computing the area at infinite level. So it would be infinite product, okay, from where n is equal to 1 to infinity. Okay, and we're going to have this pattern. 2 times 4 times 4 times 6 times 6 times 8 all over 3 times 3 times 5 times 5 times 7 times 7, so on and so forth. Okay, as you can see, it's almost the same as the Wallis product. Okay, the only difference is that the Wallis product starts with 2 number 2s. Okay, for the Wallis product we have 2 times 2, but here for the area at the infinite level we just have 1 2 in the numerator, 2 and then 4 times 4. Okay, and that brings us to our discovered identity. Okay, where the area at the infinite level is equal to Wallis product W over 2. So finally, we have here a comparative table tracking our values side by side across each level. As we can see here, as n increases or the level increases, the geometric area shrinks while the Wallis product expands. Alright, so as n approaches infinity, so we have here area at the infinite level. That will be approximately equal to pi over 4, approximately equal to 0.7854. While for the Wallis product at infinite level, the value approaches, or the infinite product approaches to pi over 2, and that's approximately equal to 1.7 or 1.5708. Ultimately, this data confirms our core discovery that the carpet's limiting area stabilizes at exactly half of that of our classical Wallis product. Alright, so thank you everyone for watching this video, and I'll see you in the next episode of Visuals with Maan. Bye for now!